way to discuss the relationship between the integration and differentiation today. Okay. For that we will need to also revise one more thing. While discussing the properties of the integrals, we had discussed the so called domain division property, namely we had seen that if you take any c in the interval a to b, then integral a to b f d alpha is equal to integral a to c f d alpha plus integral c to b f d alpha. Okay. What we want to do is that we have proved this when c is in the interval a to b. Okay. What we want to do is that something like this is true regardless of whatever is the relative positions of a, b and c. Okay. And to do that, first of all we have to make one more convention. Okay. See, so far wherever we discuss an integral like this, okay, we have always assumed that a is less than b. Okay. We have always assumed that a is less than b. Now we want to remove that restriction because that is convenient for some of the calculations that we will do subsequently, namely that a and b can be anywhere, that is b can be equal to a or b can be less than a also. So if a is equal to b, we will take this interval to be integral to be 0. Okay. So that is the first thing. If a is less than b, this case the integral is defined in the usual manner. Okay. If a is equal to b, then integral a to b f d alpha, this we take as 0. Okay. And the reason for this is obvious, because that interval has a length 0, all subintervals also will be of length 0, so all the sums, upper sums, sigma sums, everything will be 0. So it's quite makes sense to take this value as 0. Okay. The question is what we do if b is less than a. If b is less than a, what we can say is that what we will do is the following. Okay. We can always talk of integral from b to a, that is a well defined thing in the previous case. Okay, because so b is less than a, and then we will take that integral a to b f is negative of that. Okay. By convention we will take that, that is we will say that integral a, in this case integral a to b f d alpha, we will take that as minus of integral from b to a f d alpha. Okay. This is a well defined number because b is less than a. Okay. So you take that integral and take the minus of that and take that as integral from a to b f d alpha. Okay. Alright. Now what is the advantage of this convention? See, here what we can do is that, for example, what is the meaning of saying that c is in a b? It means that a less than c less than b. Okay. Right. And in this particular case we have proved this. Okay. Now what I want to say is that if we follow this convention, we can remove this restriction on a, c and b, and whatever be a, b and c, okay, this equation will be always true. Okay. That is what we want. It is a minor observation, but only thing is that for that the function should be integrable on some interval which contains all these 3 points a, c and b. Okay. So let us start with that observation. Okay. If f is integrable over some interval containing all these 3 points a, b, c. Okay. Then if f is integrable over some interval, then it is integrable over all subintervals. That is something we already seen. Okay. That is something we have seen while proving this. Okay. So that I will not state once again. Okay. Right. So that I want to say that so it will be integrable over all the intervals a, b, b, c, a, c, c, a, whatever it is. Okay. Then integral a to b f d alpha is equal to, say, integral a to c f d alpha plus integral c to b f d alpha. Okay. Now to prove that we will make various cases depending on the relative positions of A, B and C. Okay, let us take this case 1 as the normal case. Case 1 is A less than B, sorry, A less than C less than B. Okay, but this is the case we already proved. Okay, so that we did not discuss. Okay, so this is already proved. Okay, what are the other possibilities? There are several other possibilities. We shall discuss just one such possibility, and the proof in all the other cases will be similar. Okay, so for example, this C may be outside. Suppose this is the interval AB, and let us say C may be somewhere here. Okay, okay, that is okay. Let me call that as case 2. A less than B less than C. Okay. Then in this case also we want to say that this holds. Okay. In this case also we want to say this holds. Okay. But you can see that what we can do is that we can use case 1. Okay. Okay. So I can say that integral over A to C must be same as integral over A to B plus integral over B to C. Okay. That is something we can always say. So like I said, by case 1, integral over A to C is f d alpha, that is same as integral over A to B f d alpha plus integral over B to C f d alpha. Okay, all right. Okay, but what we want is in this, what we want is integral from C to B. Okay, integral from C to B, and here what we are getting is B to C, but C is bigger than B. C is bigger than B, so we use this convention here. Okay, whenever we take B less than A, integral A to B f d alpha is minus integral B to A f d. So this integral B to C f d alpha is nothing but minus integral C to B f d alpha. So using this we will get integral A to B f d alpha minus integral C to B f d alpha. Okay, and that is all. Okay, you bring that to left side. Okay, bring that to left side, you will get integral A to B f d alpha is on the right hand side, and you will get that integral A to B f d alpha is equal to integral A to C f d alpha plus integral C to B f d alpha. So that is this. Okay, so even when C was here, still this equation is true. Okay, right, and once you understand this idea, you can then deal with all other cases. Okay, suppose C is less than A less than B, again you can similarly follow, and all the other relative positions of A, B and C you can take care of. Okay. Basically you use this case 1 and this property. Okay, that is why this convention is useful. Now let us go back to our discussion on the relationship between integration and differentiation. Okay, and let me state what I had stated in the last class once again. Suppose f is Riemann integrable over AB. Over AB, and we define, so again we use the fact that whenever f is Riemann integrable, it is integrable over all the subintervals. Okay, so if we take an interval, if you take any x in AB, it is also integrable over the interval A to x. Okay, so we using that we define big F from AB to R by this big F at x is equal to integral A to x, or small f. Okay, now I should use some other variable, small f at t dt. This is for x in AB. Okay, then what we want to say is the following, that this function big F is continuous. Okay? This function big F is continuous, and if small f is continuous at some point, then at that point this big F is differentiable and its derivative is same as the value of the small f at that point. Okay, so this is the first thing. Then big F is continuous on AB. This is the first thing. In fact, we can show that it is uniformly continuous, but you can notice that that is not a big thing, because any continuous function on a closed at bounded interval is uniformly continuous. So that is something that you already know. Okay, all right. So I could have stated that big F is uniformly continuous, but there is no point, because that is, we are not saying anything new by saying that. Okay, what more? Next, what I want to say, that if at some point, okay, if let us say if F is continuous at some point, let us say x naught in, okay, let us take open interval, then big F is differentiable at x naught and derivative, that is big F prime at x naught is equal to small f at x naught. Okay, and in proving this we shall use all this whatever we have seen, because here we want to find the values of the integrals with respect to different positions of a, b and c. Okay, all right. Have you heard of what is meant by Lifshitz condition and a function satisfying Lifshitz condition? Okay, and whenever a function satisfies Lifshitz condition, it is uniformly continuous, right? You know all these things. Okay, in fact, we can prove that this function big F satisfies Lifshitz condition. Okay, and that will automatically imply that it is uniformly continuous. Okay, all right. So since this small f is Riemann integrable, we know that it is must be bounded in particular. Okay, and so I can say that if f is bounded, mod f is also bounded, and a kind of argument that we have used very often, we shall say that there exists some k, okay, there exists, we can say that there exists some k bigger than 0 such that mod fx less than or equal to k for all x in AB. Okay, so this is something we shall use. Okay, in fact, this will be our Lifshitz constant. Okay, so now consider any 2 points x y in AB, then okay, let us say first okay, let us look at fy minus fx. Fy minus fx. Okay, this is the thing, but according to our definition, integral a to y ft dt minus integral a to x ft dt. Okay, now here is the, this is just, we have just used definition. Okay, because big F at any point x is integral a to x ft dt. Now here we use this property. Okay, I want to write this as integral a to x plus integral x to y, right? And you can see that it does not matter whether x is less than y or y is less than x. In all such cases we can write, that is why we discussed those things earlier. Okay, so I can say that integral a to y ft dt, this is same as integral a to x ft dt plus integral x to y ft dt and minus this. integral a to x ft dt, okay, right. And what is to be done after this is clear, okay, this cancels with this. So what we will get is integral x to y ft dt, okay, right, okay. And now you look at this mod fy minus fx, this is same as absolute, there is mod of x plus integral x to y ft dt, okay. And remember we have proved earlier that if mod fx is less than or equal to k, then mod of the integral is less than or equal to k times b minus a, k times the length of the interval, okay. So this must be less than or equal to k times whatever is the length of the interval, either y minus x or x minus y, okay. Both, if x is less than y, it will be less than or equal to k times x y minus x. If y is less than x, it will be less than or equal to k times x minus y. So in both cases I can say that this is less than or equal to k times mod y minus x, okay, and this is true for every xy in AB, okay. So this shows that this big F satisfies this Lifshitz condition, okay, with this Lifshitz constant k, right, okay. So this big F must be uniformly continuous, or even otherwise you can just use the epsilon delta definition. If you are given epsilon, you can choose delta as epsilon by k, okay. So when this mod y minus x is less than delta, mod fy minus fx will be less than epsilon, okay. So it is not absolutely essential to recall the properties of Lifshitz continuous functions, okay, but that is what we are using here. Is that clear? Okay. So this part is easy, that is showing that big F is continuous, okay. Now we shall go to the proof that big F is differentiable at those point where small f is continuous. Now this proof will become very easy if we assume that this small f is continuous everywhere in the interval, okay. If we assume that small f is continuous everywhere in the interval, then the proof will become very easy. Let me just indicate what will happen. If small f is continuous, we have also proved what is called mean value theorem, okay. We had also proved what is called mean value theorem for the what does the mean value theorem say, that if you take integral a to b fx dx, it will be, there will exist some number c in between such that it is same as fc into b minus a, and that you can use for any interval. So in particular one can use it for the interval x to y here, okay. Fy minus fx is integral x to y ft dt. So suppose this small f were continuous, I could have said that this is equal to f at some point lying between x and y multiplied by y minus x. Suppose, okay, suppose let us take the case when x is less than y, okay. Suppose a less than or equal to x, less than y, less than or equal to b. In this case I could have said that fy minus fx is integral x to y ft dt, okay. And by using mean value theorem, we could have, okay, instead of that let us say okay, okay, this much is true. See, in order to look at the derivative, we look at f at x plus h minus fx, right. So suppose we do that here, suppose I take y as x plus h, then f at x plus h minus fx, that will be same as integral x to x plus h ft dt, okay. And if this small f were a continuous function, if this small f is continuous function, then you can write that this is same as f at some point. Suppose I call that point xi, okay, suppose I call that point xi, such that this is same as f at xi multiplied by this y minus x, in this case x plus h minus h, so f xi into h, okay, where what is xi? Xi lies between x and x plus h, okay, xi lies between x and x plus h, okay. And so we would have got f of x plus h minus big F at x divided by h, that is equal to f at xi, where xi lies between x and x plus h. Okay. Now if small f is continuous, we can say that as h goes to 0, xi will go to x. So the limit of the right hand side as h goes to 0 is fx. So the limit of the left hand side also exists, okay, and that limit is same as small f at x. Okay, so that would have proved that big F is differentiable and its derivative is same as small f throughout the interval, and that is how the proof is given in many of these undergraduate texts in calculus. Okay. That is, if you assume that small f is continuous, it is fairly easy to prove, okay, right. Okay. But we are not assuming it here. Okay. We are assuming that f is just Riemann integrable. Okay. So we will need some extra work here, right? And again this property we are proving just pointwise, that if f is continuous at just one point x naught, at that point big F is differentiable and its derivative equals to the value of the small f at x naught. Okay. Now let us see how that can be proved. Again let us take x naught and h such that both x naught and x naught plus h both should be in AB. Okay. So consider, okay, let us come back to this little later. We want to prove that this big F is differentiable and big F prime at x naught is equal to small f at x naught, and we are given that small f is continuous at x naught. So this information we have to use. Okay. This information, now what is the meaning of saying that small f is continuous at x naught? Let us use this epsilon delta definition of continuity. See, first of all it means that, okay, small f is continuous at x naught means this, that limit of fx as x tends to x naught is equal to f at x naught. Okay. Okay. And what we want to prove is this. What we want to prove is this, that limit of big F at x naught plus h minus big F at x naught divided by small h, limit of this as h tends to 0, this limit exists and that is equal to small f at x naught. This is what we want to prove, right. Okay. We are given that some limit exists and its value is something, and we want to prove that some other limit exists and its value is something. Okay, right. So we will use this, so it is convenient to use this epsilon delta definitions here. So let us say that let epsilon bigger than 0 be given. Okay, epsilon bigger than 0 be given. What is our aim? We want to prove this, right. So for this epsilon we want to find a delta, such that whenever this mod h is less than delta, the difference between this whole expression minus f of x naught, that should be less than epsilon. Okay, that is our aim, right. Okay. But what do we know? We know that there exists some delta such that whenever the difference between x and x naught is less than delta, the difference between fx and fx naught is less than epsilon. Let us record that first. Okay. So there exists delta bigger than 0 such that mod x minus x naught less than delta implies, that is whenever mod x minus x naught is less than delta, mod fx minus fx naught is less than epsilon. Or which again means that whenever x belongs to the interval x naught minus delta to x naught plus delta, this happens. Okay. Now we will choose, see, suppose we choose that choose h such that mod h is less than delta. Okay. Choose h such that mod h is less than delta. Okay. So we want to show that for this h, the difference between this and this must be less than epsilon, okay, right, okay. Let us write the value f of x naught plus h, big F of x naught plus h minus big F at x naught. Okay, we can use this calculation here. Here you take this as x naught plus h, this as x naught. Okay, so we have shown that that is the thing, but integral from x to y ft dt. So this is nothing but integral from x naught to x naught plus h ft dt. Okay. Okay. What we want is this divided by h. Okay. So this divided by h will be 1 by h into this. Okay. And what we want to show is that the difference between this and f x naught, that is less than epsilon. Okay. All right. So I will write that also here. Okay. I will just what we want is minus f at x naught. Okay, I will rewrite this. Okay. Minus f at x naught. What was this? It was 1 by h integral from x naught to x naught plus h ft dt. Okay, and minus f x naught, right. Okay, right. Okay. Okay. Now this is a small observation here. See, suppose I just take this integral from x naught to x naught plus h dt. Okay, what will be the value of that? That will be h. So I can say that this is same as f x naught by h into integral from x naught to x naught plus h dt. Okay, f x naught is a constant, right? F x naught is a constant. So if I want, I can take it inside the integral sign also. Okay, I can take it inside the integral sign also, which I will do. Okay, so doing that and simplifying, what we will get is this whole thing will be 1 by h into integral x naught to x naught plus h ft dt. Now ft minus f x naught, ft minus f x naught dt. Okay. Okay, do you agree with this? Okay. Then what we want to show is that the absolute value of this whole thing is less than epsilon. Okay. Okay. So we will take the absolute value. Okay, we will take the absolute value. Absolute value of this, it's same as the absolute value of this, and that is again same as the absolute value of this. Okay. And okay, one can say further that this is equal to 1 by mod h into absolute value of this integral x naught to x naught plus h ft minus fx naught dt. Okay. But we have proved that absolute value of the integral, okay, is less than or equal to integral of the absolute value, right. That is something that we have proved already. So we can use that also. So this is less than or equal to integral 1 by mod h integral x naught to x naught plus h mod ft minus fx naught dt. Okay. Now the main question, what can we say about this mod ft minus fx naught? Okay. See, remember t lies between x naught and x naught plus h, and mod h is less than delta. Okay. See, t is in the interval x naught to x naught plus h, and mod h is, so it is clear that t must lie between x naught minus delta to x, in fact t must lie between x naught minus delta to x naught plus delta, and we have seen here that if if in that case that means it is clear that mod t minus x naught is less than, in fact mod t minus x naught is less than mod h, which is less than delta, okay. So mod f t minus f x naught must be less than epsilon, okay. So this must be less than epsilon, okay, and so the value of the whole integral must be less than epsilon into the length of the interval, which is h, okay, which is h or mod h, okay, depending on whatever, okay. So this whole thing is less than epsilon times mod h divided by, okay, this is less than 1 by mod h into epsilon times mod h, right, okay, or okay, which is same as epsilon, right. This is what we wanted to show, right, that is given epsilon there exists delta bigger than 0 such that whenever mod h is less than delta, the difference between this whole expression minus f x naught is less than epsilon, okay, which is same as this, okay, right, okay. Since we did not assume that small f is continuous, we had to do some extra work, and similar thing you will also observe in something that we will prove next, okay, which is also called fundamental theorem of integral calculus, because that is the one which relates that is the theorem which shows that the process of integration and differentiation are in some sense inverses of each other. So let us just state the theorem first. Fundamental theorem of integral calculus. Okay. All right. Again, we start with an integrable function. Suppose f is Riemann integrable, okay, integrable over AB, okay, and okay, we want to consider a function whose derivative is this given function small f, whose derivative is a given function small f, okay. Normally I would have used the letter big F for that, but we have used that already for something else and we want to use that also in our proof, okay. So I shall use some other letter, okay, and suppose f is Riemann integrable over AB, and let us say and g from AB to R is differentiable and g from AB to R is differentiable and g prime is equal to f, okay. That is the derivative of g, it is same as small f, or if you want to write in the full form, that is same as saying g prime x is equal to fx for every x in AB, okay. Then the conclusion is this, then integral a to b fx dx is nothing but g at b minus g at a. And why this is called fundamental theorem? There are so many reasons, okay. One reason I have been saying right from the beginning, that in the definition of the integrals we never use derivatives, okay, right. But we observed that using the definition of the integrals very few functions can be integrated. So to find the value of the Riemann integrals, this is the most useful theorem, okay. And this gives a method. What does it say? That find some function big G whose derivative is this function that you started with, okay. Such a function is, okay, you might call it antiderivative, or sometimes it is called indefinite integral or anything like that, okay. It is some function whose derivative is the function that you started with, and once you find that function, the value of the integral is nothing but value of that function at b minus value of that function at a, right? And so you can also now use this notation which you normally use in calculus, that is this is nothing but gx between a and b, okay, gx between a and b, okay. So that gives a method of finding the value of the Riemann integrals, okay. That is why fundamental theorem. Again here also, if we assume that this function small f is continuous, then the proof will be very easy, and that is how it is given in most of the books dealing with the undergraduate calculus, okay. How the proof will be easy? Suppose we assume that small f is continuous everywhere, okay. If small f is continuous everywhere, then we have proved using this, we can show that this, then that means this big F is also differentiable everywhere, okay. Big F is differentiable everywhere, and then its derivative is nothing but small f, okay. But what does it mean? That is, it will mean that this big F prime at x is fx, and that is same as big G prime at x for every x, okay. Or in other words, it will mean that if you look at the difference big F minus G, its derivative is 0 for every x in AB, right, okay. And we have already seen that if the derivative of a function is 0, the function must be constant, again using mean value theorem, okay. That means this will imply that big F minus G is equal to some constant, suppose I call that constant k, okay, suppose I call that constant k, okay, or which means, okay, that is, or this is same as saying that big Fx minus big G at x is equal to k for all x in A, okay. So in particular one can say that if you look at integral a to b ft dt, whether you call fx dx or ft dt, that is same ft dt, this is same as big F at b, right, big F at b, okay, right. But at any point the difference between big F and big G is same as k, okay. So I can say that big F at b, suppose I apply this for x equal to b, you will get this as k plus G at b, right, okay. Now the only question is what is k, okay, only question is what is k. To do that you apply, you take x is equal to a, okay, you take x is equal to a, so it will also give that big F at a minus big G at a is equal to k, okay. But what we know is that big F at a is 0, okay. Look at the definition of big F at a, it is integral, if x is equal to a, it is integral from a to a, that is how we started today's class, okay. Big F at a is 0, okay, so which is same as saying that k is equal to minus Ga, okay, that is same as saying that k is equal to minus Ga, so you put it back here, so you will get this as Gb minus Ga, okay. So again let me caution you that this is not a proof of this theorem, okay, but if you assume the extra assumption that small f is a continuous function, then the proof becomes very easy, and then that is how the proof is given in many of the undergraduate level books, okay, because there you always assume that small f is continuous, okay. But since we are not assuming that, we will have to do some extra work, you know, and that extra work will involve the several things that we saw about the Riemann sums, okay, the relationship between integral as a limit of sum, that is what we will have to use, okay, right. So to do that, let us consider a partition, let's consider some partition P, okay, suppose P is a partition with this property a equal to x naught less than x1 less than xn etc, xn which is equal to b, okay, right. Then okay, you look at this Gb minus Ga, okay. GB minus GA. Okay, in this notation it is same as GXN minus GX naught. Okay, we can add and subtract the in between terms. Okay, I can write this as GXN minus 1, then plus GXN minus 1 minus GXN minus 2, etc., etc., and coming to that I will write this last term as GX1 minus GX naught. Okay, in other words, I can write this as sigma I going from 1 to n GXI minus GXI minus 1. Okay, all right. Okay, now we have assumed that this big G is differentiable on the whole interval. Okay, so we can apply mean value theorem to this big G. Okay, by mean value theorem what will happen, this you can say this GXI minus 1 that will be same as G prime at some point in between multiplied by Xi minus 1. That point I will call Ti. Okay, that point I will call Ti. Okay, so we can say that by mean value theorem, Lagrange's mean value theorem, there exists Ti in the interval Xi minus 1 to Xi such that G at Xi minus G at Xi minus 1 is same as G prime at Ti multiplied by Xi minus 1. Okay. Okay, but what is G prime at Ti? Look at here. Okay, for each x, G prime x is fx. Okay, so G prime at Ti is nothing but f at Ti. Okay, G prime at Ti is nothing but f at Ti. So this is nothing but small f at Ti, and this is what we have been calling delta xi, xi minus 1. Okay, that is nothing but delta xi, right? Okay, so what happens to this? This becomes sigma I going from 1 to n f at Ti multiplied by delta xi. Okay, f at Ti multiplied by delta xi. Okay, and now what is this? It is nothing but Riemann sum for the function f and for this. So this is nothing but RPF, right? That is what we have denoted. Okay, this is nothing but RPF for this choice of the points Ti, this choice of the points Ti. Okay, right? Okay, okay. But what we know is that this function f is Riemann integrable. Okay, and if the function f is Riemann integrable, we know, we have already shown that the limit of this Riemann sums as mesh of the partition goes to 0 exists, and its value is same as integral a to b fx dx. Okay, so what we can say is that this tends to integral a to b fx dx as mesh of p tends to 0. Okay, whereas this left hand side is independent. Whatever is the partition, this will remain the same. Okay, so which means in the limit these two must be equal. Okay, so we can say that taking limit as, is that clear? This whatever I have done till now is true for every partition, whatever be the partition. Okay, it doesn't depend. It's a, this GB minus GA turns out to be a particular Riemann sum for every partition. Okay, and so take the limit as the mesh of the partition goes to 0. Okay, so that is same as integral a to b fx dx, and hence it must be same as GB minus GA. So taking limit as mesh of p tends to 0, we get integral a to b fx dx as g at b minus g at a. Okay. Okay, so that establishes the fundamental theorem of integral calculus. Okay. We need to do one more thing now. See, till now we have been talking about the Riemann integrals as well as Riemann's tilde integral whenever we take a function alpha. Okay, we also want to establish whether those two are related to each other. Of course, one thing we know, that Riemann integral is a special case of Riemann-Stieltjes integral, but there are some other cases also in which you can establish the connection between the Riemann integrals and or you can reduce the Riemann-Stieltjes integrals to the case of Riemann integrals. Remember this, why we want to do that? Because this fundamental theorem of integral calculus we have now proved only for Riemann integrals, we have not said anything similar for the Riemann-Stieltjes integrals. Okay. So suppose we can reduce a Riemann-Stieltjes integral to Riemann integrals, then one can use this fundamental theorem and find the value of that. Okay. So that is the idea, and the question is when we can do it. Okay, let me just give the conditions, call this as a theorem. Okay, suppose f is Riemann-Stieltjes integrable or AB alpha with respect to this function alpha, which we always assume to be monotonically increasing. Okay. All along we assumed that this function alpha is monotonically increasing. This means f is Riemann-Stieltjes integrable with respect to the function alpha. Suppose this function alpha has some additional properties, then we can say that the two integrals are the same. Okay. If alpha is differentiable, and not just differentiable, this alpha prime is Riemann integrable. If alpha is differentiable and if alpha prime is Riemann integrable, over AB, then what we can say is this integral a to b. Of course, I can also say that then f into alpha prime is Riemann integrable. This is something I need not have said separately, but it follows. Okay, integrable, and Riemann-Stieltjes integral of this function f coincides with the Riemann integrable of this function f into alpha prime. Okay, or if you want to write in the symbols, what it means is this, and integral a to b f d alpha is same as integral a to b fx alpha prime x dx. Okay. Now, so this says, remember this, what you have on the left hand side is a Riemann-Stieltjes integral, integral a to b f d alpha, and what you have on the right hand side is Riemann integral. Okay. But Riemann integral of a different function, this function f alpha prime. So what does the theorem say? That if alpha is differentiable and if the derivative is Riemann integrable, then one can reduce a Riemann-Stieltjes integral to a Riemann integral. Okay, and once we do that, we can, if this function satisfies these conditions also, if you can find some function g whose derivative is this, then we can use fundamental theorem of calculus to evaluate this Riemann-Stieltjes integrals also. Okay, that is the idea. Now I shall not give a very detailed proof of this, I will just give you the main idea, because considerations involved are somewhat similar here. Okay, let us again look at the partitions and see what is the corresponding Riemann-Stieltjes sum is. Okay, but before that, is that first of all this part is clear, f alpha prime is Riemann integrable, f is integrable, alpha prime is integrable. So we have already shown that if the two functions are integrable, their product is also integrable. Okay, so f alpha prime is integrable, that is clear. Okay, that is something that we have already shown. So only thing remains is why these two values are the same. Okay, so just look at one particular Riemann-Stieltjes sum. Suppose I look at say R P f alpha. So what will be that? This will be sigma I going from 1 to n f at Ti multiplied by delta alpha I. Okay, multiplied by delta alpha I. Okay. Now what is delta alpha I? Delta alpha I, let me write it in the full form. It will be alpha at xi minus alpha at xi minus 1. Okay. Alright. Now we know that alpha is differentiable, so we again use mean value theorem. Okay, alpha is differentiable, so we again use mean value theorem and write this alpha xi minus alpha at xi minus 1 as alpha prime at some point in between those two, okay, and multiplied by xi minus 1. So this will be, only thing is that we cannot say that that point is same as ti, it can be something different. Okay, it can be something different. So suppose I call that point as si, so we can say that this is the argument by mean value theorem, there exists si in xi minus 1 to xi such that alpha xi minus alpha xi minus 1 is equal to alpha prime at si multiplied by xi minus 1, right. Okay. So we shall use that fact here, sigma I going from 1 to n, this is f at ti multiplied by alpha prime at si multiplied by this xi minus 1, I can write that as delta xi. Okay, all right. Okay. Now if this si were same as ti, I could have said that this is the thing but the Riemann sum of corresponding to f alpha prime, okay, f alpha prime, but that is not the case, okay, and that is why we need some additional work. But what we will do, we will do the usual thing in such a case, we just add and subtract alpha prime ti, okay. So we will write this as sigma I going from 1 to n f ti multiplied by alpha prime ti multiplied by delta xi, then okay this I will plus sigma I going from 1 to n f at ti. What we need to do is, this is alpha prime si minus alpha prime ti multiplied by delta xi. Okay, is that correct? That is f ti. I have added and subtracted alpha prime ti, alpha prime si minus alpha prime ti, okay, and this, since we have already shown that f alpha prime is Riemann integrable, we already said that f alpha prime is Riemann integrable, this will go to this will go to integral a to b fx alpha prime x dx, this will go to fx alpha prime x dx, okay, and what remains is to show that this can be made arbitrarily small, this difference can be made arbitrarily small. I shall skip the proof of this because the time is over, you can read the proof from this book. The point is that f alpha prime is Riemann integrable, and if you write these things separately, both turn out to be the Riemann sums of the same integral, so the difference between them will be small. That is the essence of the argument, okay. So with that we will stop here, okay. As I said, I will not give the complete details of the proof, but this is the idea, okay, that is basically main idea is to add and subtract alpha prime ti, okay, and then show that whatever the difference is there from this to this difference can be made arbitrarily small, okay, that is the idea. I will stop with that.